Okay, continuing on with the Pythagorean Theorem, we're going to take a look at the converse of the Pythagorean Theorem and what that all means. And why does the Pythagorean Theorem only apply to right triangles? Well, the word converse means opposite. So when we talk about triangles, and right triangles specifically, if the only other thing other than a right triangle could be an obtuse triangle, which is right here, or an acute triangle, which is here. And we can kind of take a look based on our square analogy with the Pythagorean Theorem, and that is, when we had the squares, when this was a 3 by 3 square and a 4 by 4 square, we could see by that they would all fit into that 5 by 5 square. But we can tell with an acute triangle, if we were to put squares around the sides, we can see that the leg triangles the squares, or the amount of units that would fit into there, will exceed the amount of units that would go into that square of the hypotenuse. So what Pythagoras figured out then was that the sum of the legs were larger than the hypotenuse when everything was squared. And conversely, with an obtuse triangle, he found that the hypotenuse, that square that was in the hypotenuse, was so large that these squares of an obtuse, these legs of the obtuse, there wouldn't be enough of them there. So in reference to the Pythagorean theorem, the legs would be smaller than the hypotenuse. So he was able to use this to help to talk about other types of triangles as well, but not to be as exact as he could be with right triangles. So again, let's take a look at that one more time. So we're talking about a right triangle, and we know that a right triangle is that the theorem applies as a squared plus b squared equals c squared. When we take a look at an acute triangle, the sum of the legs, once they're each squared, add them together, will be larger than the square that's going to be on the hypotenuse side. With an obtuse triangle, the sums of the legs, once they are squared, when they add it together, will be smaller than the hypotenuse. So we're going to try a few problems and some numbers, and I'm going to give them to you in order. So as I give them to you, it will be A, B, and C. So I have the square root of 11, 5, and 6. So this would represent A, B, and C. And if I was to draw that triangle, and again, we don't know what the corner is. We don't know what that size is. But I know that one leg is 11, square root of 11, one side is 5, and the hypotenuse is 6. And I'm going to use the Pythagorean theorem to help me determine what kind of triangle this is. So I'm going to look at a squared plus b squared, and I'm going to leave an open circle there for c squared, because I'm not quite sure what sign's going to go in there. Remember, my choices are equals, less than, and greater than. So I'm going to drop in the numbers as I see them. I see the square root of 11 squared plus 5 squared, and then the relationship to 6 squared. Now for most of us, the 6 times 6 is easy. That's 36, as is the 5 times 5, which is 25. What throws us is the square root of 11 squared. So let me offer a thought to you. The square root of 25 squared, which is similar to the square root of 11, but I think we can look at this and solve it, and it'll make you understand where everything is coming from here. So in order of operations, we always do the parentheses first. So inside the parentheses, we have the square root of 25. We know that the square root of 25 is 5. Next, after we do parentheses, we do exponents. So 5 times 5 is 25. So after simplifying this, we can say that the square root of 25 squared is 25. What that reveals is that I pretty much ended with what I started with. That means that when you take the square of something and the square root of something, it is the opposite of each other. It's like taking 2 steps forward and 2 steps back. You end up in the exact same place. So with that thought in mind, if I'm looking at the square root of 11 squared, when I reduce that or simplify that, it's only going to give me 11. So I continue. 11 plus 25 is 36. And since both sides are exactly the same, I know that I have a right triangle. We're going to try it a few more times. Once again, here is a triangle with sides of 7 and 9 and a hypotenuse of 10. So we put it in the formula, 7 squared plus 9 squared. And again, how does it relate to 10 squared? We know 7 times 7 is 49, and 9 times 9 is 81. And 10 times 10 is 100. Well, 81 plus 49 is equal to 130, and that is greater than 100. So that we're saying the legs are larger than the hypotenuse. Well, if for that to be true, that means that we have an acute triangle because the legs are larger than the hypotenuse. A couple more tries at this. Here I have 6, 10, and 13, A, B, and C. 6 squared plus 10 squared, and how does that relate to 13 squared? Well, 6 times 6 is 36, 10 times 10 is 100, and 13 times 13 is 169. Well, here I have 136 on one side and 169 on the other. I know that 136 is smaller, so it's saying that the hypotenuse is larger than the legs put together. That tells me that I have an obtuse triangle. We'll try it one more time. 7, 11, and the square root of 170. So the legs are 7 and 11, and the hypotenuse is the square root of 170. We know that the square root of 170, just for information, is 13.08, and on and on and on. Pardon me, I stand corrected. 13.04, on and on and on. So we have 7 squared plus 11 squared. How does that relate to the square root of 170 squared? Well, 7 times 7 is 49. 11 times 11 is 121. The square root of 170 squared, remember, these are opposite of each other, so they undo each other, so that puts us at 170. 49 plus 121 is 170, so since both sides are equal, these are the dimensions of a right triangle. Hope that you can now understand the converse of the theorem and how it applies.